We are now recording. Let's get the slideshow set up for our current slide. And then I'll ask again, any questions on anything we've covered so far? All right. I can't remember, Tia, is this your, yeah, this is your first class in here. Hi. Do you know all about the syllabus? It's the same as in physics class. It's out there under Blackboard, under content, the syllabus, the research paper instructions, the locator card, all the PowerPoints for this course, web sources that other students have given me or I found that they said they found useful in the course, and also the YouTube videos. And the YouTube videos, if you click on that, you can go back and hear everything we've done so far in the course. It's everybody, not just Tia, since she hasn't been here. And that's when I talk about the syllabus and the research paper and all that. Let me get a name, please. Ivory, got it. Okay, good deal. All right. The top three in the alphabet are here, the bottom three in the alphabet are here, and one person in the middle is here. Ah, here comes another. Yeah, Sakina. Shakina, I'm sorry. Without the H. Okay. So any questions before we get rolling? All right. Oh, you even have one here. Or foot 9. Okay. Here's one. Okay, 3 at the top, 3 in the bottom, and 3 in the middle. So we got our 9. Hopefully we'll get some more in. Break double digits here. Okay. I think what I'll do first is blow this up. Okay. It seems so long since we met last, a week ago. We were talking about the intermediate value theorem, and that was the last thing we did, and if you got your text, it's on the same page, somewhere around page 100, depending on which edition of the text you have. Middle of the page, Theorem 1, Intermediate Value Theorem. If f is a continuous function on some closed interval a to b, then for every value m in between f of a and f of b, anywhere in that interval, there exists at least one value c in the open interval a to b, such that f of c is equal to the m. Okay? And here's the example. Prove that this equation, sine x, is equal to 3. Okay? Now, by the way, that's what we call a conditional equation. Sine x is equal to 3. Okay? It says prove that that equation has at least one solution. Okay? Now, they don't give us an interval. Okay? It says we may apply the IVP, intermediate value theorem, because f of x equals sine x, this function here, is continuous everywhere. You can pick any interval you want from minus infinity to positive infinity. Sine is continuous everywhere. Okay? Now, they happen to choose an interval from 0 to pi halves to illustrate. It's fine. No problem. So prove that this has at least one solution. Okay? First thing you do, show that it's continuous. Sine function is continuous everywhere. Okay? We choose an interval where we expect a solution to exist. Okay? Now we could have done something bigger, like 0 to 2 pi or minus pi to pi, because we know those are one complete period of sine. We just know that because we know our trick, right? They happen to choose something smaller than that, which is fine because we knew this too, for between 0 and pi halves. So we choose an interval, and one of the reasons they chose that interval, we suspect a solution to exist. One of the reasons we chose that is we know that at x equals 0, sine is 0, and the x equal pi halves, sign is 1. Okay? So, 0.3, which is what the equation asks for, sine x is equal to 0.3, is between 0 and 1. So therefore, since it's a continuous function on this interval, the closed interval 0 to pi halves, then there's got to be at least one place between 0 and pi halves on the interval here where the function value is between 0 and 1. In other words, is 0.3. There is one, and in this case, only one. If we had chosen a bigger interval, there would have been yet another one here. A bigger interval here, there would have been another one there. Yeah, because this is a repeating, function. There are an infinite number of places where that's true. But on this interval, we're guaranteed to be at least one, because f of 0 is 0, f of pi halves is 1, 0.3 is between 0 and 1, so therefore there is at least one value c on the interval 0 to pi halves where it has to be equal to 0.3. They didn't ask us where it was, they just said prove that there is a function there. Okay? That's all they're asking for. You can tell me what that is. Pull out your calculator, do an inverse sine. Okay? So the intermediate value theorem, IVT, can be used to show the existence of zeros of a function if f is continuous and takes on both positive and negative values. Then you know there has to be a 0 in between. If f is positive here and negative here, there's got to be a 0 in between if it's a continuous function in that interval. Now, if this were a tangent function and the interval spanned from pi fourths to 3/4 pi, you can't guarantee anything because tangent is not continuous on that interval. It is between negative pi fourths and pi fourths. That would be perfectly fine there. But it wouldn't be from pi fourths to 3/4 pi because it has an infinite discontinuity at pi halves. So you have to be careful that you have an interval on which the function is continuous. If you do, intermediate value theorem pertains. Does that make sense? So that leads to, I hope, corollary 2. All right, existence of 0, basically what we just said. If f is a continuous function on some closed interval a to b, and if f of a and f of b are non-zero, that's one requirement, and have opposite signs. F of a could be negative, f of b positive. Now notice, a and b don't have to be opposite signs. F of a and f of b have to be opposite signs. Or f of a could be positive, f of b negative. They just have to have opposite signs. Of course, they can't, either one of them be 0. Okay? So if they have opposite signs, they're non-zero, and have opposite signs, that f of x has to have the 0 somewhere on that open interval a to b. You know it's not at the end point, f of a or f of b, because they're non-zero there. But one's positive, one negative. Can't get from there to here without crossing the x-axis. Therefore, it would have a 0. Does that make sense? All right. Pretty simple example. Oh, this relates to that. The bisection method, it's called. Show that the function, this is not this function. Oh yeah, okay. It may be. Show that the function f of x is equal cosine squared, cosine squared x minus 2 sine pi x over 4. Show that has a 0 on 0 in 0 to 2. Okay? Between 0 and 2, x equal 2, show that this function has a 0. Okay? How are you going to determine that? Well, first you have to just indicate that this function is continuous. Cosine is continuous. Cosine squared is continuous. Sine is continuous. Sine of 5 or x over 4 is continuous. Doesn't matter. Those are both continuous functions. Sum, difference of continuous functions, multiples of continuous functions, they're continuous. So nothing, no problem there. So how would you show this has to have the zero? Now, the question here, show that it has a zero on that interval. The problem is the next part. We'll get to that. How do we show that it has a zero? Let's pick the endpoint. 0 and 2. What do we need to show that? What does the corollary say? Have to have opposite signs. So let's see if they do. F of 0. I can do that one without a calculator. Cosine of 0 is 1. 1 squared is 1. Sine of 0 over 4 is 0. Sine of 0 is 0. 2 times 0 is 0, so 1 minus 0 is 1. So, this one is positive at this endpoint. Let's go to the other endpoint. Here we have a little bit of an issue, don't we? It says cosine of 2. What does that mean? 2 what? Radians, not degrees. The only way that could be degrees if you saw a degree sign on it. When it says 0 to 2, it says 0 to 2 degrees, then you know it's got to be in radians. Remember in calculus, in physics, and a lot of things, unless they specify that they're talking about degrees, you better assume radians. Okay. Lauren, right? Okay. Just had to find you in this. All right. So, I can't do this one in my head. I can do this one in my head. I can't do this one in my head. What is cosine of 2? Anybody know? You gotta have a calculator on this. That calculator better be in what mode? Radian mode. Frankly, whatever it is, we're squaring it, so it's not, you know it's got to be positive. Okay? Actually, I could do this, okay. This has got to be positive, and it's got to be positive less than 1, though, right? Because cosine is never greater than 1. Square 1, and you still get 1. This, however, sine of, what is 2 over 4? 1/2. Well, again, you're in radians. So, yeah, we've got to have a calculator here, I think. Yeah, I could think through it and probably make this work, but let's use our calculator. What do you get when you plug in 2 for x here? Anyone done it yet? Cosine of 2 squared minus 2 times cosine of 0.5. Or your calculator sure is slow on it. Those black boxes. What do you get? Negative 0.4, okay? That doesn't quite look like what they got, but yeah, it could be, okay? Anyway, it's a negative number. That's all it took, folks, to show that you got a 0 in between. At one end of the interval, you got a positive value. Second end, you got a negative value. It's a continuous function. It's got to have a 0 in between. Until we get to the next part. Then locate the 0 more accurately using the bisection method. What in the world do we mean by that? Okay? Now, I hope you still got that on the screen, that you didn't throw it away or something. let me get my pen activated. Boy, this computer is slow today. Okay. We know that f of 0 is equal to 1. And we know that f of 2, what did you say it was equal to? Negative 0.4? 0.4? Okay? Everybody got that? Only one person did it? Okay. 0.4. Okay? How do we go about finding the 0 then? Well, I know it's positive here, negative there. Let's take a value halfway in between 0 and 2. How about 1? Plug that one in. Cosine squared of 1, be sure you're in radian mode. Cosine squared of 1 minus 2 times sine of 1/4, 0.25. So let's do f of 1. What does that give you? Plug in a 1 here and a 1 there. Cosine squared of 1 minus 2 times sine of 1/4. Radian mode, what does that give you? Negative 0.3? 0.2, okay? So this is negative 0.2. Guess what? We can't guarantee, there could be, but we can't guarantee that there's a 0 here, but we know there's a 0 between those two, don't we? Because one's positive, one's negative. Bisect it again. Now let's do a f of 0.5. Okay? What do you get? Okay? That would be cosine squared of 0.5, radian, be sure you're in that mode, minus 2 times sine of 0.125, I believe that's 1/8. 0.5 over 4 would be 1/8. That would be 0.125. What do you get there? Anybody? This time we're plugging in 0.5 here. Cosine squared of 0.5 minus 2 times sine of 0.125. Now, if you like using fractions, you could do that. Cosine squared of 1/2 minus 2 times cosine of 2 times sine of 1/8. Whatever you prefer. Just easier to me to punch in on a calculator the decimal form. Anyone get anything yet? 0.5. That sounds reasonable. 0.5. Okay, what does that tell us? Our 0, we don't guarantee there's one between 0 and 0.5, but we are guaranteed there's one between 0.5 and 1. Well, what's the value between 0.5 and 1? Between 1/2 and 1. Let's go a little higher. That would be between 0 and 0.5. 0.75, or 3/4. Plug that in and see what you get. Again, cosine squared of 0.75 minus 2 times sine of, what would that be? 3/8, which would be 0.375. .1 something? 0.16? 0.16. And these are all probably approximate, I'm pretty sure, right? Okay, still positive. That means we have a 0 between 0.75 and 1. This is positive here, negative there. We keep looking, okay? And the 0.75 is here. Looks like we're going to be really close there. So let's do, what's a bisect between 0.75 and 1. That would be 3/4 and 1. That would be 7/8, right? 0.875. 875. Okay? Plug that one in. Negative 0. What? 02. You know what? That's close enough to 0 to me. Okay. For government work, I'll do it. To the nearest tenth of a digit, that's a 0. Okay. And sure enough, it looks like that's awfully close. 0.7, 3/4 would be somewhere right in there. That's going to be very, very close. If you want it better, keep going. This time you would go between 0.7, 3/4 and 7/8. That'll be so many 16ths. Go there. Keep zooming in on it. Actually, for decimal purposes, what I think I would do, between 1. I would go 0.9. That would be a lot easier than doing fractions. Okay, just do 0.9, and then you have 0.9 to 1. Keep going. If it's in between that, 0.95. If it's the other, just keep going until you can see which way it goes. Now, that's sort of like a limit, isn't it? We were talking about those earlier. This sure is getting more like this. Good old, I told you about Archimedes, didn't I? What he called this kind of method? Not doing this. The method of exhaustion. I mean, you just keep narrowing it down, narrowing down, bisecting until you say, hey, I'm tired, that's as close as I need to get, I'm going to stop there. Method of exhaustion. Now, is this the way you find the 0 of a function? No. Good old Isaac Newton, who developed calculus, came up with a far better way than this. And we'll talk about that a little bit later. It's called Newton's method. And that's what your calculators do, by the way. Don't most of them have a thing of finding a 0? They do Newton's method. And they get there really, really quickly. Of course, they do a lot quicker calculations than you did, I'm sorry to say, but you did. Okay. So that's the bisection method. Okay. So it's some number between 0.75 and 0.875. Is that right? Yeah, 0.875 was negative, 0.75 was positive. You could keep going if you wanted to. So I would have done the next how about 0.8? That would have been between those two. And then keep narrowing down. All right. Conceptual insight here that intermediate value theorem seems to state the obvious, namely that a continuous function cannot skip values. Yet its proof, which is given back in Appendix B, is far more subtle than that. I mean, it seems so obvious, but to prove it, it really depends on a lot of things, completeness property of real numbers, and a variety of things like this. To highlight the subtlety, observe that the IV intermediate value theorem is false for functions defined only on rational numbers. So in other words, if you have a function that's not defined for irrational numbers, then you can't say it, because how can you say it's continuous if you have gaps? Okay, so you just can't do it. F of x equal x squared is continuous, but it does not have intermediate value property if we restrict its domain to rational numbers. Okay. Enough of that. Summaries there. Now, I can't remember, did y'all like doing preliminary questions or not? I'll be glad to do them if they're beneficial to you. Yay or nay? I saw nays. Okay. If you like to see them, it's pretty good conceptual stuff. So homework exercises, do any of the odds 1 through 5. I think I assigned those before. And then any of the odds 7 through 15. Do 17, another intermediate value problem exercise, and then do 19. Do either 21 or 23, or both if you choose, either 25 or 27, or if you choose both. 29 is not so much of a calculation problem as a think-through problem, so if you want to think through that, you certainly can. Now, I've heard it called something else. Further insights and challenges, I never assigned those, but if you find those are interesting or challenging and you want to do them, by far go for it. Number 34 talks about the ham sandwich theorem. Now, in my experience, it's always been called the sandwich theorem. I don't know why this book, he must like ham sandwiches, he took it one more step, the sandwich theorem. If you can find that, and you find that an interesting topic to write on, go for it. Which reminds me, don't be forgetting your research paper. I mentioned it just briefly earlier. I've had one class, afternoon class, that I believe 2 or 3 people have turned in research papers. My morning classes, none. Okay, so folks, don't forget your research paper. All right. Oh, here we go. I'm sorry, they had a table. What we were just doing, they had a table here. I could have saved you. I didn't want to save you any work. No, I didn't say that. They show between 0 and 1. I don't know if these are the numbers you were getting. The midpoint was 1/2. Alpha 1/2 was 0.5 something. Alpha 1 was -0.2. Assume that's what y'all are getting. I don't remember. I think y'all got 0.4. So that single, I don't know. It still doesn't look like what they showed in the book. And then you go, so you know it's between these two. So they picked 0.34. That's positive. So now we know it's between those two. So they picked 7/8. And when they did that, we got here. So their conclusion is it lies somewhere between 7/8 and 3/4. 7/8 was negative, 3/4 was positive. So therefore it's in between that. Everywhere else, you put the bigger number on the bottom and the smaller number on top. I don't know why they're reversed here. But between that. And you can keep narrowing it down as much as you like. Okay. That finishes the slideshow for 2.8. Let's move on to 2.9. Any questions on 2.8? Last section here, and I think I've mentioned to you before, I don't know why it's taking so long to open. PowerPoint is being extraordinarily slow today. Back when I took calculus many decades ago, this is where we began. We began with limits, of course, but when we did limits, my professor started with the formal definition. None of this arm waving, oh, look how this works. He started with this formal definition, which is somewhat, I think, of a pain in the neck. But let's go. Something we've already done. Okay? In this section, we re-examine the definition of a limit in order to state it in a more rigorous and precise fashion. Why? We used weasel words before. Remember when we stated it before? If we said, as long as the absolute value between f of x and L becomes arbitrarily small when f is sufficiently close to, those are sort of weasel words. What do we mean by arbitrarily small? What do we mean by sufficiently close to? Okay? I think D'Alembert was the one who did not find those kind of statements very satisfying, mathematically satisfying, so he came up with a lot more of a formal definition. And here it is. And by the way, this came many decades after calculus was invented. They didn't really have a rigorous theoretical platform for it. They knew it was true. I mean, Newton wouldn't have proposed it if it hadn't been. But the rigorous proof came much, much later. Okay? And this type of proof is called analysis. If any of you are math majors, are you? Okay, you will be doing lots of rigorous proofs. Most of you pre-engineering, you just want results, right? That's what engineers are after, so go for it. Okay. From our definition, if we were saying, and we've already shown this, we showed it numerically, we showed it graphically, that this is true. But we haven't proven it rigorously, okay? So we say that the limit as x approaches 0 of sine x over x is equal to 1. Like I said, we did it numerically, we set up a table of numbers, got closer and closer from the left, from the right, they were approaching 1. We showed the graph of it and showed there's a hole at 1 at x equals 0, but that hole is at x equals 1 and it's approaching either way. We know that's the case, or at least best we can show. Okay? How do we do this rigorously? Okay? Now, I don't know if you remember what we said about it before, but and this just still seems to be going in circles somewhat, but I can't write on that slide. I have to shrink it down to this really tiny little slide here before I can write on it. What the statement was that as f of x, which in this case is sine x over x, approaches 1, okay? In other words, the absolute value between sine x over x and 1 is sufficiently small or close enough to 0 or something like that. That's the thing. It was f of x, absolute value of f of x minus L. That's how we talked about it. Where f of x was sine x over 1, L was your limit, that was 1. Okay? So we're saying as that gap between those two values, now these are y values again. This is the function, f of x equal y, that would be that value. We say it's getting closer to that. So as the function gets closer and closer to this, as you get x closer and closer to 0, then that gives you the limit. So you see your x is going closer to whatever this is. X is approaching 0, this is approaching 1. So as x is closer and closer to 0, that's getting closer and closer. F of x getting closer to 1 in this case. Okay, your limit. Now, they do, again, the graphic illustration of this, and it seemed like to me we already beat this to death, but they're showing it again. As x gets closer and closer to 0, who cares about what's happening out here? I mean, things are happening, but who cares? We're interested as x gets close to 0. So this figure shows it looks like it's going to 1. Well, let's just start with not all this stuff, but narrow it down. Get closer and closer to 1. So as x is getting closer and closer to 1, x getting closer and closer to 0, the f of x is getting closer and closer to 1. The gap, f of x minus 1, here is less than 0.2. And x is 1 unit away. The interval, absolute value of x less than 1, meaning that negative 1 less than x less than positive 1. If you're in this gap here, within 1 of 0, you're guaranteed that you're within 0.2 of 1 of them. Okay? So, again, they do all this kind of talking about it, and frankly, it doesn't show me much. But then, what if you shrink and say, I want to get closer than 0.2. I want to get within 0.004. Can we do that? Well, let's see. Let's just zoom in. Okay? we're wanting to get this not within 0.2, but within 0.004. Okay? Now they've really cut this down a lot, and they're only showing just a little bitty portion of this, but blowing it up. Well, sure, if we have this within 0.004, meaning between 0.996 and 1, that's all you're showing here. If you get your x within 0.15, you're going to fit the bill. Because if you plug this in here, this in there, negative 0.15 here, 0.15 here, yep, then you got it. So what they're getting at here, if you choose some value here, I want this to be that close to the y value, then if you can find an x value that gets you that close, then you know the limit has to exist. Now, if you kept getting down here, and when you got really, really close, you found out there was a gap there. It's not happening here. But if you found that out, no, you couldn't get within that this one actually, if you really zoomed in on it, and you found out this one came in here, and this one came up there. Well, then if you got within here, you couldn't ever bridge that gap because they're coming differently. But if you always, no matter how small you choose this to be, you can always find some value here that will get you within that limit, then that says the limit exists. That's what they're getting at here. If you chose 0.2 was close enough, yeah, you got there in a few steps. If you said 0.004, I want to get within that, then just keep cutting this down until you're within that. In other words, reduce the size of the difference between x and 0 to 0.15, and you get within 0.006. If you wanted it with 0.001, get even smaller, okay? 0.001 would be this one. Well, something about there would work. Okay. That's what we're getting at pictorially. Again, that's not a rigorous proof, but that's where the rigorous proof is going. Okay? So here is the formal definition of a limit. And again, boy, my professor made us know this. He didn't make us know it by heart, but you almost had to be able to sing it in your sleep, because this is what he did every time. Suppose you have a function, f of x, defined for all x on some open interval containing some number c, but it's not necessarily equal to c. It may not be defined at x equals c, but it's defined in some open interval that contains c, but not necessarily at x equals c, just like we did before. That function, sine x over x, is not defined at x equals 0, because you can never divide by 0. Not even in an indeterminate form, you still can't do it, okay? So, that limit, as x approaches c, that's what's happening on the domain side. The limit as x approaches c of f of x, that's on the range side, is equal to L. As x approaches c, we're saying f of x is getting closer and closer to L. Okay? When does that limit exist? Here's the formal definition. That's true if for all epsilon greater than 0. In other words, choose some small value epsilon. Okay? Small value epsilon, as small as you want it to be. For all epsilon greater than 0, there exists some delta also greater than 0, such that, okay, if you choose, no matter how close to 0 you get, but it has to be some positive value within 0, the absolute value between f of x and L, you can choose this as small as you want. This has to be greater than 0. You know, can't be equal to 0, but as close to 0 as you want to get. For the absolute value of this, less than epsilon, that is guaranteed to be within that range of epsilon if the 0 is less than this difference here, x minus c, is between 0 and delta. Okay? If you, no matter how small you choose the epsilon, if you can find a delta making that true, then the limit exists. Okay. Now, some examples, that's a really easy thing to do. In others, it's a pain in the neck, okay? But you can do it, okay? Is it worth it? For huge pains in the neck, I wonder sometimes. But others, it's pretty simple. Let's do this one. Let f of x equal 8x minus 3. Plus 3, sorry, I can't read. Okay? And what the question is, they want us to formally prove, A, that the limit as x approaches 3 of f of x, anyone want to make a guess what you think that is? 27. Okay, 27. Because plug it in, plug it in. It's a continuous function. Yeah, everything we said should work, but we want to prove that's true. Okay? Because when you plug in x equals 3, 8 times 3 is 24, plus 3 is 27. So how do we do that? Okay? We used to almost have to recite it. This is true for every epsilon greater than 0, or any epsilon greater than 0, okay? There exists a delta. This is true if and only if this is true. A delta greater than 0, such that for absolute value of f of x minus L less than epsilon, if 0 is less than absolute value of x minus 3, that would be a C there, less than delta. Okay. We want that to be true. Okay? There is an epsilon. No, for every epsilon greater than 0, you can find the delta that makes that true. Okay? Now, how do we go? Since we're given the first, let's start with that. Your f of x is 8x plus 3. Okay? Minus 27. That's your limit, right? This absolute value we want less than some epsilon. So given there's an epsilon greater than 0, we want that to be true. Well, that's not hard to do, is it? This would be absolute value of 8x minus 24, right? Less than epsilon. You choose as small epsilon as you want. We want to guarantee that's in there. Well, we can do this. 8 times x minus 3, right? Less than epsilon. Well, absolute value of 8 is 8. Pull that outside. 8 times absolute value of x minus 3 is less than epsilon. Right? Well, guess what? Divide both sides by 8. You have shown there is this, set that equal to delta. You've shown there is a delta, so you can guarantee that this is true for any value epsilon you choose. There's a delta. If you chose 0.001 for your epsilon, then divide that by 8, and that's your delta. That guarantees you within that. No matter how tiny you make that epsilon, you can guarantee this because this is true. This is less than delta. So for any epsilon you choose, there is a delta that makes that true. Okay? If that's true, that limit exists. Well, of course, we knew it existed anyway because it's there. You plug it in and it exists. Okay? So, oh, and they did the same number I did. They chose epsilon 0.001. Now, why did I choose that? A lot of time in statistics, if you want to really show something's true, you can't show it's always true, but for any, within an interval, they call it sometimes a confidence interval or a t-test or something like that, 0.001. If you can show it that, most of the time anyone will say, okay, that's close enough, And if you got your epsilon 0.001, you just had to get a delta that's within 0.000125, okay? Yeah, that would work. Okay. Now, if you see, they started the same way we did. For every epsilon greater than 0, this has to be true if and only if this is true. Okay? That's where we started, and then they showed that's true for delta equal epsilon over 8. You choose an epsilon, I can find a delta that'll make it true. That means the limit exists. You can't get too small an epsilon for me to find it. I can always find it, because in this case it's always just, no matter how small an epsilon you give me, I'll take 1/8 of that, that'll be the delta, it'll work. Okay. Here is the picture, which is pretty similar to what we had before, but maybe in a little bit better term. What are we dealing with? Now here's your 8x plus 3. This is the function we're dealing with. What if you said not 0.001, but I wanted to make sure if I choose an epsilon of 0.2, okay, can you give me a delta that makes that happen? Well, 0.2 would be, say the limit is 27, so this is going to be between 26.8 and 27.2. You've got to be within that band. Well, here's the function, y is equal to 8x plus 3. That's a good old linear function defined everywhere. Well, that's going to be defined if you choose a delta that's again, take 1/8 of this and you get this. And they say this is not drawn to scale. Obviously not, because this is 27 here, that's 3 there. I mean, that's obviously not drawn to scale. Okay, but if you pick something within 0.2 here, you're going to have to get between 0.025 here, and you're guaranteed that's going to be there. That means the limit exists. No matter how small you choose that, you can find the delta below like that. Okay? So you don't really, you choose how close you want this to be, your answer to be. That tells you how close you got to be on your input. Get what your output is, how close is that? If you can find an input that guarantees it, the limit exists. Okay, are they all that easy? You better believe they're not. Okay, nowhere close. Okay. Here's example 2. I really find these way more tedious I think they're worth, but if you're into proving, this is basically what you have to go through. So we're trying to prove, let me write the problem down, they didn't write it down. So sorry about this, I got to shrink it. Okay, prove that the limit as x approaches 2 of x squared is equal to 4. Guess what, team? There's no doubt that, there's absolutely no doubt about it. But if you want to do a formal proof of it, boy, what a pain in the neck that is. Okay, so what would we have to do? For any epsilon greater than 0, no matter how small you choose, there exists a delta, I abbreviate like crazy, which is also a small positive number delta greater than 0, such that the absolute value of x squared minus 4 needs to be less than that epsilon whenever 0 is less than x minus 2 is less than delta. Okay? If you choose an epsilon, you've got to be able to then find a delta that's going to make it happen. Okay? Now, last time, pretty easy. This time, not so much so. What would be the first thing you would do to that? First thing to come to mind to simplify this. You're trying to get something that looks like that, by the way. What could you do to this to make it look something like that? Factor! Exactly. And what does that give you? X plus 2 times x minus 2. Okay? All right. Now, this is where things get a little hairier. Okay? Now, you're trying to get to this. What you got is something over here that's in the way. Okay? And x plus 2. If that were out of there, then you would be in fine shape. Okay? So what they do, because we're going to require that that part be small, the x minus 2 be small, we may as well assume, and this is where it sort of gets you. Okay? Assuming. Okay? In the Navy, we used to have a saying for that. We won't go into that now. But, which means that we assume at the outset that x minus 2 is less than, say, 1. Okay? Why did they choose that? Well, you're going to treat it really small, so let's just say it's less than 1. Well, 1 is not all that small. You can get a lot smaller than 1. 0.5, 0.3, 0.2, 0.03. Yeah, you can get a lot smaller. So let's just assume that the x minus 2 is less than 1. So there's an assumption. X minus 2 is less than 1. So in other words, a delta of 1, you say, no problem with that one. Okay? It's got to be considerably less than that. Okay? Now, if that's the case, the x minus 2 is less than 1, and that's less than 0, what we can do, absolute value of this less than 1. Okay, let's start with that. So that means that minus 1 is less than x minus 2 is less than positive 1. That's what absolute value means. The absolute value of x minus 2 is less than 1. That means that negative 1 is less than this, and positive 1 is greater than that, right? It's got to be between those two. That's what absolute value means. Absolute value less than 1 has to be in there. Well, what we're going to do is add 2 to both, all three sides of that inequality. So add 2, add 2, add 2. That says that 1 is less than x is less than 3. Okay? So the x is going to be between 1 and 3. All right? No problem there. Okay. Now, if that's the case, and again, this can take so much time to prove something that's so obvious, okay? This is what we're shooting for, to get that, okay? Sorry. Okay? Absolute value of x squared minus 4 less than your epsilon, okay? And there is a theorem, and they kind of gloss over that, okay? That this is equal to absolute value of x plus 2 times absolute value of x minus 2. I really don't think that's true. I think it's less than or equal to, but they're saying that. Okay. Now, if we plug in our values we had before, okay, the x has to be between these. That means this part here has to be between 3 and 5. This one here. If x has to be between 1 and 3, x plus 2 is between 3 and 5. Well, if it is, then this thing, x squared minus 4, has to be less than 5. Let's take the larger of those two times x minus 2. Okay? All right. So this thing here has to be less than or equal to that. But remember, this has to be less than or equal to 0. So this thing has to be less than or equal to 0. Okay? So therefore, this thing we're looking for is, this has to be less than epsilon. So we can divide this by 5. Okay. So on the one hand, absolute value of x minus 2 is less than epsilon over 5. Okay? Now that would be if your delta was less than 1. Remember, that's where we had to assume. So there we found out with the epsilon. So if you choose an epsilon greater than 5, that won't work because your delta would be greater than 1. But as long as you choose an epsilon less than 5, this will give it to you. Okay? So kind of a pain in the neck to go through all that to get there. And if you thought squaring it made it a pain in the neck, just wait till you see the next one. Okay? Oh, and by the way, here's the figure of that one. And again, it's sort of, I swear, when I was doing this in college, I thought, is this really what they call a rigorous proof? It looks like they're just sort of shuffling numbers around. But really, it was a rigorous proof, okay? So here's the graph, f of x equal x squared. You can choose a delta such that f of x lies within an epsilon of 4, okay? Now, that's a huge thing, okay? No, I'm sorry. Within epsilon of 4, I'm sorry. For all x between 2 minus delta and 2 plus delta, okay? And again, this is just showing the picture of what it's supposed to be. But if you choose an epsilon, pick me a small epsilon. 0.5? Fantastic. That was less than 1. Okay, less than 5. Okay. All right, small enough, 0.5. Okay, so this would be between 3.5 and 4.5. You want to make sure you're within that. Okay, well, divide that by, you said 0.5, divide it by 5. Is that what we did? 0.5 divided by 5 would be 0.1. So you choose the delta that's within 0.1, then you're guaranteed you're going to be there. So sure enough, that would work for you. Okay? And again, this is just a picture of what those are saying. If you choose an epsilon within this, then this delta is going to work and guarantee you get within that. Okay. Now, like I said, that was enough of a pain in the neck. Oh, wait, I'm sorry. Still go to this. Absolute value of x squared minus 4, that was your function minus limit. f of x minus L, that's in your parentheses, less than epsilon if the 0 is less than absolute value of x minus 2, that's as x approaches 2, that's where that comes from, where delta is the smaller of epsilon over 5 or 1. Remember, we assume it's going to be less than 1. And if it is less than 1, or if it's greater than 1, then it's got to be less than epsilon over 5. So we came up with the epsilon over 5 or 1 of those two. And by the way, most of the time your epsilon is going to be 0.5 or something like that, so you're almost always going to be less than that first assumption, 1. I should have blown this up. Okay. So you see you actually have a 2 case there. Either 1, okay, or epsilon over 5. And most of the time your epsilon is going to be small enough, that's going to be the lesser of the two. Okay. Here's the next one. Might as well just do it here. Prove that the limit as x approaches 3 of 1 over x is equal to 1 over 3. Now, you look at that and say, that's a duh. Of course it is. As x gets closer to 1, as x gets closer and closer to 3, 1 over x is closer and closer to 1/3. Pretty obvious, right? Okay? If you try to do a formal definition, oh my word, what a pain in the neck this becomes. Okay? The formal definition is for every, I'm not going to write all this out, epsilon greater than 0, there is a delta, that's supposed to be there, is a delta greater than 0 such that the absolute value of 1 over x, that's your f of x minus 1/3, your limit, for this less than epsilon, yuck, been writing so many graders down, less than epsilon, there is a delta such that for this to be true, that 0 less than x minus 3 less than delta. Okay. Now, what you want to do is get this thing to look something like that, right? Okay. What would be your first step to get this to look something like that? Say again? Okay, excellent. Common denominator, and that would be 3x. Okay? And what would be your first numerator? 3 minus x less than epsilon, right? Okay. You know you're not too far off, especially since 3 minus, in absolute values, 3 minus x, x minus 3 is really the same thing, right? Absolute value, doesn't matter which order you do it. It's that 3x in the denominator is sort of the pain in the neck, okay? So, again, what you do here is, so this thing here is absolute value of 3 minus x, which, by the way, is the same as x minus 3, because you're dealing with absolute values anyway. And then what you have here is 1 over 3x. And you want that less than epsilon, right? That's what we're going to, okay? Well, this looks just like that. So again, you're required for this to be small. How small? Want to pick a value? How about what we did before? Less than 1, right? That limit there has to be less than 1. So x minus 3 less than 1, which means the absolute value of that, so let's make it between minus 1 and 1. So again, let's do the little trick of adding 3 to all 3 sides. Okay, and that would be 2 is less than x is less than 4. Okay, so you're guaranteed that thing to be less than 1 anytime x is between 2 and 4. I mean, that's pretty obvious. Okay, so you can get your epsilon small enough if your delta is less than 1. Okay, that's doable. Okay, now okay, that's this part, less than 1. What about this part? If you chose this limit, that would be 1 over 6. If you chose this side, that would be 1 over 12. Which of those is greater, 1 over 6 or 1 over 12? Sorry. Which is greater? Okay, we got this part less than 1. Okay, this part then would have to be either this, plug in either the 2 or the 4 here. If you plug in the 2, you get 1 over 6. Plug in the 4, you get 1 over 12. Which of those is larger? 1/6. Okay, so we're going to go with 1/6. So if you choose, then that part, your absolute value of this part right up here, this now becomes the absolute value of f of x minus 1/3. Sorry, less than 1/6 x minus 3. Okay? Well, guess what? That's your epsilon. Set that equal to epsilon. Well, then multiply both sides by 6, and you get absolute value of x minus 3 is equal to 6 epsilon. Okay. So, in this case, give me as small an epsilon as you want to give me. Okay? Either the delta's got to be less than 1, which is what we did at the beginning, or it's got to be less than 6 epsilon. So if you gave me an epsilon less, what did you give me before? 0.5? 6 times epsilon would be 3. Well, then the delta just got to be less than 1. Oh, that's great. But if you gave me a real small one, then your delta has to be less than 6 times that, which would be, that has to be the lesser of 1 or 6 epsilon. So whatever your delta is, that gives it to us. Okay? And I think that's what they say in the next slide. So the absolute value of this, that's just, I'll blow this up a little bit. And again, this is sort of a pain in the neck, but it almost seems like you're setting it up so it has to be true, but you really are. That's what you're doing. This is your absolute value of alpha of x minus L. That has to be less than epsilon. For any epsilon greater than 0, that has to be true. And that's true if this thing, which we just carried it through, delta is the smaller of 6 epsilon or 1. So if he gave me an epsilon of 0.5 here like he did last time, then you choose your delta to be the lesser of 3 or 1, that would be 1. So you would choose the 1 in that case. If you gave me the epsilon to be 0.01, okay, then 6 times that would be 0.06. Ha! Look, I'll go with this one. Delta just has to be the smaller of those two. Okay. That's your formal definition. Now, this in some small ways illustrates kind of the bizarre nature of what we just did. Oh, I'm sorry. No, it doesn't. This is going to something else. I thought this was going to be that one. It wasn't. They didn't show a graph of that one. Sorry. Now, they've sort of jumped to, oh, okay, this is graphical insight. Sorry about this. keeping a graphical interpretation of limits in mind, if this is your function, okay, and I don't know what function that could be. It's got all sorts of little squiggles in the middle. It's probably some really esoteric function. The only requirement is it's got to be continuous. And if that function is continuous, no matter what it's doing in between there, okay, you can, for any epsilon that you choose, you can find a delta that is close to that C. Doesn't even have to be defined as C, but you go close to the C, and you can guarantee you're within that. If this function is not continuous, has a jump discontinuity, now if it has a removable discontinuity, you're fine. That's fine. But if it has a jump discontinuity, an infinite discontinuity, or any of those that are not fine, like other than a removable discontinuity, you can't do it. You can't give me, for any epsilon greater than 0, if you give me an epsilon something in between here, you're never, ever going to be able to close the gap. Okay? And no matter how small the gap is, just give me an epsilon inside that gap, you'll never close it. Okay? Sure, this will work for this delta, but, you know, an epsilon here, never going to find anything that will connect those two. So function, if the function is not continuous, x equals c, the gap is always larger than some value, and they just happen to take the midpoint between the two. If it's that, you can't ever close the gap. Ever. Ever. So that won't work for a discontinuous function. Now, the next thing they do here is proving the limit laws. You know what? I had no problem with the limit laws the way they were. Do we really have to prove them? Well, they're doing it. And again, just for completeness sake, let's do so. Remember, the limit was, the sum limit law was the limit of a sum of two functions if both of them had limits. If f of x had a limit L, if g of x had a limit L, M, then the limit of the sum was the sum of the limits. Okay? And this statement here, the formal proof says the sum of these is equal to the sum of the function of the limit of sum would equal the sum of their limits. So that would be this. So this thing would have to be less than 0. Well, guess what? We already assumed that limit existed. And that limit existed. So when you figure out what put them together, then this is always less than that. Now this, by the way, is sort of an expression they call the triangular limit, that you can split something like that up, and it's always going to be less than or equal. Okay? No matter whether L is plus or minus or M is plus or minus, it doesn't really matter. It's always going to be less if you separate the two. And that is called, oh, they don't give a name of it here, okay? But they say other proofs are given in Appendix D, and I think they show that. No, they give it in the margin over here on the left. The triangle inequality, that's what I was looking for, that name. Of course I'm going to have to shrink this. Here's the triangle inequality. Absolute value of A plus B is always less than or equal absolute value of A plus absolute value of B. Now if you think about that, it's got to be true. Okay? Give me an A, give me a B. Give me an A. Any value. 1, a B. Second, 1 also. Okay, absolute value of 1 plus 1 is 2, and that's equal to absolute value of 1 plus absolute value of 1. Okay, 1 plus 1 is 2. Yeah, that would be equal to. But what if B were negative 1? What is this absolute value then? 1 plus negative 1 would be 0. That would be less than absolute value of 1 plus absolute value of negative 1 would be 1. 1 plus 1 is 1. 2. So yeah, it's going to be always less than or equal. So the signs could flip or flop or anything else, but it's always going to be less than or equal to. So that's why they could split this one and this one and this, split it into two absolute values by the triangular inequality that guarantees that to be true. But that limit we knew existed. That limit we did. Those were the givens in the sum law. So therefore, you've just shown that the limit of the sum is less than or equal to the sum of the limits, okay, by the triangle inequality. The others are given there too. If you did the formal definition, okay, then and again, this sounds like they're, I hate to say it this way, but it almost seems like the smoke and mirrors, but it's not quite. It's actually better than that. If this limit is less than or equal to epsilon, okay, that was what you do. It just assumed that the first one of those was epsilon over 2, the second is epsilon over 2. You could have done it the other way. If this one was less than epsilon, that was less than epsilon, then make this 2 epsilon, then make your new epsilon, epsilon. I mean, you can play around with it and wiggle things around. It still works. You can choose epsilon as small as you want to, including epsilon over 2. That's even smaller. So if it works for epsilon over 2, it'll work for anything. So again, it's almost is so obvious, you say, why do they mess with it? But they do. Okay. Again, it's kind of a thing they do, formal mathematical analysis. You would need to be fiddling with those, the formal definition. Again, preliminary questions, worthwhile or not? Want to do them or not? Yay or nay? No? Okay. Homework exercises, then do any of the odds. Looks like 1 through 17, if I'm looking at them right. And I wouldn't just skip over some of these. Do some of the earlier ones, and then maybe some that are a little more esoteric. But see if you can work some of those. Don't let it frustrate you, but use the examples as patterns. Then do any of the odds 19 to 23, and then wrap it up with any of the odds 25 to 29. Okay? Further insights and challenges, they take you into uniqueness theorem and that kind of stuff. So that pretty much is going to wind up chapter 2. At the end of chapter 2, there's also chapter review exercises, and if I'm not mistaken, these answers are in the back of the book as well, I believe. Let me make sure. Yeah, odd numbers are in the back. So if you want to do a few more, just to familiarize yourself, 1 or 3, cover some of the early stuff, any of the odds 5 through 9, any of the odds 11 through 49, a whole bunch there. Any of the odds 51 to 57, any of the odds 59 to 63, '65, any of the odds 65 through, I guess, 79. And again, you determine how far you want to go with that. All right. Notice a couple people did take a mini break. How about let's taking a very short 1 to 2 minute break just to stretch, go use the restroom, get a good drink of water, something like that. I will pause this. Let's see, how are we doing on time? Aren't here and are listening. I just passed out the test, and I won't go over, but I told everybody what I think. Number 1 was from 2.1. Y'all correct me on this. Number 2 was 2 and 3 from 2.2. Okay. 4 and 5 were from 2.3. 6 was from 2.4, right? 7 was from 2.5. 8, at least 8A was from 2.6, and 8B could have been 2.5 or 6. I didn't give you anything from infinite, and 9 is from 2.8, and 10 is either from 2.9 or anywhere else in the chapter you want to give up. Okay? Now, and as I was saying, the test is due 1 week from today, technically. However, if you need more time, you can have it. Just don't hang on to it till the end of the term or something stupid like that. Please get it in as soon as you can, because guess what? I can't return anybody's test to them. I'll let you see your test as soon as I grade them, which hopefully will be within a week of the time you turn them in, or by the end of that week. But I can't return them to you until I get them all in. So don't be holding on to your test and keeping me from returning everybody else's to them. So get them in as soon as you can. Certainly use as a rule of thumb before I give the next test, because the next test may depend on this. If you miss things here and you haven't had a chance to figure out why you missed it, then you're already at a disadvantage for the next one. So please get them in sooner rather than later. Okay? So what I was just starting to say is that's the reason I give you homework exercises. If you have been doing the homework as we went along, this test is probably going to be a piece of cake. If you haven't been doing the homework as we went along, you've already lost your piece of cake. You got to really chew on this stuff. Okay, so take advantage of doing the homework. It makes life easier later. Okay, but I will work any homework exercise. If that's your question, you don't know how to approach a problem like this, find one like it in the book. I'll do anything in the book. I won't do those. You have to figure out those. Does that make sense? Okay. All right, let's move on to chapter 3. Differentiation. This is the heart, to me, of Calculus 1, differentiation. Now, we'll do a little more stuff later, and all of it builds on this, but the limits led up to this, and everything else builds on this, so this is the heart right here. Okay? And guess what? Have we seen this before? It seems like we've seen it in 2 or 3 other sections here. Okay? We're still doing limits, huh? Am I in the right section? I don't think so. No. Sorry about that. I got out of this but didn't go to the right file. Sorry about that. That was something we've seen before. Okay, chapter 3. I guess I got to talking and thought I had already done this, but I hadn't. Okay. Now we have to wait for PowerPoint again. I didn't have this done already. Here we go. Now, to me, this is one of the coolest pictures. I've seen it in physics books. I've seen it in calculus books. This is actually as cool as some of them are, but it's still pretty cool. You know what that's a picture of? Say that again. Breaking the sound barrier. You're absolutely right. It's a jet aircraft that actually just at the point of breaking the sound barrier. Because if you think about it, sound is a pressure wave, and when your sound usually precedes you. You know, you can hear things in front of me because, my sound is going. Now, if I were traveling fast enough, close to the same as the speed of sound, then the sound, if I was getting closer and closer to that speed, the sound would get to you just a little bit before I would. But then, if I exceeded the speed of sound, all those pressure waves, I'd have to break through those. And there were actually some who thought you couldn't do it, the plane would fall apart. Well, obviously, we can do it. In fact, they now have Mach 1, Mach 2, Mach 3. I don't know how far up they do, several times the speed of sound. But what has happened, those pressure waves have piled together, and even though it was a clear day, there was enough moisture in the air, they got pressed together, and here he came breaking through that little cloud he created by going close to the speed of sound, and he just broke through. Calculus is the foundation for all our understanding of motion, including aerodynamic principles that make supersonic flight, which is what we call this traveling faster than the speed of sound, possible. Okay. Your book has a skydiver, okay, and you're talking about terminal velocity there. All those things depend on calculus, which basically depends. First, one area of calculus is differentiation. Okay, and here's where we begin. Now, and I think this is probably old hat to most of you, but maybe not. In math, up till now, one of the most important things we were doing was finding slopes of lines, right? Now, straight lines, they were a piece of cake, right? Change of y over change of x, rise over run, that was your slope of a line. If you had a function that's traveling along here, then you do an average change of the y value over the x value. So change of y, f of x is always y, right? Change of f over change of x, that would give you the slope of any secant line on a graph, on any kind of curvilinear function. Whatever is going on, the change of f over change of x would give you an average rate of change of that function between those values. Okay? Well, let's just imagine that as the x was going from a to x, so that's your change of x, your function was going from f of a to f of x, right? That's your y for this one, there's your y for that one, okay? So this is, again, change of y over change of x. That would be an average rate of change as the function went from a to x, okay? Now, that's all they had. That's all they had back at the time Newton was trying to do things like come up with a proof for Kepler's laws of motion, planetary motion. Average rate of change just did not do it well enough. He needed what the change was as x was approaching a. And that's what we did in limits. That's what we're doing now. So that's why you always do limits before you do differentiation, because differentiation depends on it. So you take that, and this represents, I've been doing the arm waving, here's the actual pictures for it. If this is your function, any old function, whatever function it is, okay, and it's going from a to x, here it is at point P at A f of a, that's your, a is your input, f of a is your output, the y value. At x is your input, f of x is your output. So the average rate of change between here and here was the slope of that secant line, okay, that went from those 2 points. Delta f over delta x, f of x minus f of a over x minus a. Okay. Now, if you let this Q get closer and closer and closer to P, then that secant line is going to be approaching the slope of this tangent line as the x approaches a. As x minus a approaches 0. That's your slope of the tangent line. That's your instantaneous rate of change of this function. Here's what the average rate was between here and here. What was it at that point? That was the slope of the secant line. Okay? Even though x minus a, your denominator, is not defined as x approaches a. As it gets closer and closer to 0, you can't plug a 0 in there, but you can calculate the limit, and that limit is the tangent line. And that's going to be what we call the slope of the tangent line is your first derivative. Okay? They're going to show this again and again and again. You almost may wind up getting sick of seeing it, but let's see, can I get 3 of these on? I don't think so. Close, but no cigar, so let's just do 2 at a time. Okay? So here's that same figure we had before. P to Q, slope of the secant line. As you let Q get closer and closer, that slope changes ever so slightly because Q is coming down the curve here. Okay? So there's a little bit closer. Whoops. Yeah. All that and hit the wrong key. Sorry about that. Okay, there was the first one. The second one. And then you let Q get even closer to P. Your slope of the secant line changes ever so slightly until finally you get closer and closer, Q approaching P, and when that difference goes to 0, it can't quite go to 0. In the limit it can, and in the limit you get the slope of the tangent line, the red line, okay, as Q is approaching P. Okay. Now, based on this intuition, we can define the derivative. Okay, we'll go back to our original graph here. I can't see why they keep showing the same thing over and over, I guess. Maybe from the book it makes sense to. But this is called, I don't know, for those, some of you did have pre-calculus algebra here, didn't you, at Lawson? We had pre-calculus algebra, Math 112. The rest of you probably took it, if you took it at all, you took it somewhere else. Then they have things they call difference quotients. You may not have remembered them if you did. But a difference quotient is what this is. That's the difference, f of a plus h minus f of a over a plus h minus a, which is a change of this over the change of that. Quotient, this divided by that. Difference quotient, the difference here divided by the difference here. Okay? So that's what we did. And if you write it in terms of h rather than as x approaching a, you have f of a plus x minus f of a. Then let the h get smaller and smaller. Your difference here is a plus h minus a, which is just h. And as h gets smaller, that gets smaller, then that's another way of looking at your derivative, and that, in fact, is how it's usually defined. Okay? And we'll use it both ways. Sometimes one way is a little easier on the calculations than the other, but they're both equivalent. The derivative of f of x at some point x equal a is the limit of that, the difference quotient, if it exists. If they're continuous functions, they will exist. If they're not continuous functions, they may not exist. So, and this is one symbology. Now, is differentiation new to all of you? Pretty close? Okay, some of you have had it before. They have so many ways of writing a derivative. One is the prime notation. This means first derivative of f at x equal a. And here's how it's defined. The limit as h approaches 0, remember h is that difference. F of it is a plus h minus a. So that's the difference in the second point and the first point. As h approaches 0, of f of a plus h minus f of a, there's your difference. Here's your quotient over x plus h minus a plus h minus a. That would be h. Okay? There's your difference quotient. Yes, that goes to 0. Now, of course, you can't directly plug it in. It's not defined that way. But if this is a continuous function, this difference is a plus h, and a get closer and closer together. The function's getting closer together. So this is approaching 0. As that approaches 0, then you have an indeterminate form. You may, if you do have a limit, and the limit exists, then that's going to be your derivative. So when the limit exists, we say that f is differentiable. This is its derivative. It's differentiable at x equal a. Okay? An equivalent definition, the one that we sort of started with, f prime of a, or derivative of f a, okay, is the limit as x approaches a, rather than introducing this difference of h there, f of x minus f of a, those are the two different values over the difference in the, this is your y value difference over your x value difference. Change of y, change of x, and that would give you the same thing. Your denominator approaching 0, if this is a continuous function, these two are approaching 0 too, if that limit exists. They won't always exist, by the way, but if it does exist, that's your derivative. Okay? Now, let's talk a little bit about tangent lines. We know theoretically what they are. We know graphically what they are. Let's give a little bit more formal definition. Assume that f is differentiable at x equal a. Got to be a differentiable function. The tangent line to the graph of y is equal to f of x at that point p, which is a f of a. That point p, you put an a in for x, you get f of a as your y. So that's your point. xy is a f of a. The graph of that function at that point is the tangent line to the graph is the line through point P with a slope of your first derivative. Okay? The equation of the tangent line. Now, this is nothing all that new, but it's really close. Okay? Remember, let's go back one slide. Okay? What did I say this was? Rise over run, right? So that's your slope of your secant line. The limit as x approaches a, that's the slope of the tangent line. So slope is rise over run, right? Now, how do you go? I think this is probably old hat to all of you, but if you remember, let's start anew. What is the equation for a slope, formula for a slope? Go back to algebra. y2 minus y1 over x2 minus x1, right? That was your slope formula. If you know the 2 points, you can calculate the slope. Okay? Now, the points that you know are designated by those subscripts. But what if you didn't know the 2 points, but you knew the slope, but only 1 point? Okay? Now, this is going to be, here you know both of those. x1, y1, and x2, y2. You don't know the slope. This is how you calculate it. But if you know x1, y1, 1 point, and the slope, but you don't know the equation of the line, here is the, I don't think they ever did it this way when you were doing this. Let's make your x and y the unknown and make m the thing that you do know. Okay? All right? Then what do we do with this? Multiply both sides of the equation by your denominator here. X minus x1. X minus x1. All right? These go out, and that gives you y minus y1 is equal to m times x minus x1. Now that is, does anyone remember what we called that back in the day? The point slope formula. You know a point and the slope, that gave you the point slope formula. It came directly from your slope formula. You just didn't know 2 points, you only knew 1 point and a variable. That gives you that. Okay? And then we took it another step. But if you remember that, do the same thing with this. This is your slope, your m, and these are your your change of y to change of x. That gives you basically the same formula. Y minus y. Okay. The only difference is you've just cut out the limit here, but it's still the same thing. Here's your slope. There's your change of x, change of y. y is equal to slope times change of x. This is your equation of a tangent line, will always be in that form. Okay? Now, differences is, this is not calculated by a quotient, it's calculated by taking the derivative. We haven't done it yet, but that's what we're going to do. This is just x minus a lot like it was before. This is y rather than y minus y1. You calculate y1 with plugging a into the value for the function. So, other than that, it's basically your point slope formula. And that's what they call it too. Okay, with that done, let's do example 1. What is the equation of the tangent line? Find the equation of the tangent line to the graph of f of x is equal to x squared at x equal 5. Okay? Find the equation of the tangent line. Well, does anyone remember what the equation of the tangent line was? Just was the last slide. Y minus f of a is equal to f prime of a, which is a derivative, which we haven't done yet, times x minus a. Okay, in that picture, what are your pieces up there? Well, your f is the function, x squared. Okay? What is your 5? In this formulation here, what is your 5? Your f is x squared. So this will be a squared. That's what this would become. What is your 5? Up there it's called the 5. What's it called here? A. That's your A. Okay? So let's fill in the pieces we can. F of A then would be f of 5, which would be 5 squared, which is 25. Okay. Now, what we have to do is what the f prime of A. And what did we just learn that f prime was? F prime of A was, back 2 slides, the limit as x approaches 5 of f of x. You got it. And what was your f of x? F of x is x squared. And can you take that limit for me? Yes. What is it? 25. We've got all the pieces we need now. Y minus f of A, 25, is equal to No. Y'all didn't give me the formula right. Or maybe I led you astray. This was, what was that formula? F prime of A? F of, go back a couple slides. F of what? Okay, we're doing more the f of x minus f of a, the second one of those. You see it? Yeah. Over x minus a. That's your limit, that's your derivative formula. Okay? And what was our f of x? X squared. Oh wait, let's keep the limit here. Limit as x approaches 5 of x squared minus f of a was 25. Over x minus, what's your a? 5. Right? Everybody agree? Now, how do we do one of those limits before? What was the trick? It's what again? Factor. Excellent. And what does that give you? X plus 5 times x minus 5 over x minus 5. X minus 5's go out, and the limit as x approaches 5 of x plus 5 is, say again? 10. Excellent. Now we got our f prime of a. Okay, so f y minus f of a, which is 25, is equal to f prime of a, which is 10 times x minus 5. Okay? That is your equation of your tangent line. Now, is that the neatest, nicest, prettiest form of it? Probably not. You can clean that up a little bit. Y minus 25 is equal to, distribute, and what would that give you? 10x minus 50, and then add 25 to both sides, so wipe out that, right? Y is equal to 10x minus 25. Okay? Yep, that's what they got. Now, that gave you the slope of the tangent line, that point slope formula. Okay, find an equation of the tangent line to that graph at x equal 5. There it is. There's the equation of that. Now, then they show how to do it using the other formula. You could do that as well. Just a little bit of a break here, little side note. Isaac Newton referred to calculus as the method of fluxions, okay, from the Latin word flow, flux, flux, flowing, okay. But the term differential calculus was introduced in the Latin form calculus differentialis, or something like that. It almost sounds like a medicine or something, by Gottfried Wilhelm Leibniz. That eventually won out, and that's what people call it. We don't talk about fluxions anymore. So basically, that old dispute between Newton and Leibniz, I think most people came down on the side Newton did develop it first, but we liked the way Leibniz talked about it, and we used Leibniz notation and Leibniz verbiage on it a lot more than we don't use fluxions anymore. Okay? Now, here is the graph of this function. Now, obviously not to scale. That's 3 here, that's 30, or 50 here, okay? So obviously it's not quite to scale. Okay? Not anywhere close. But it is a parabola, y is equal to x squared. 3, 0, 0, 3, 9, you can't pick that out there. 25, 25, 49, 49, yeah. Now, the blue is the graph of that function. The pink is the graph of the tangent line in this form. Now, obviously they don't bring this down far enough, but if you projected this back this way, you see, sure enough, it looks like it would cross just about at minus 25. It would. It is exactly minus 25 with a slope of plus 10. Now, it doesn't look like a plus 10 slope unless you realize that is 25 over 3. Yeah, 25 over 2.5 would be right about there, and that would be 1 to 1. So yeah, that is a plus 10 slope. Okay? And so that is the slope of the tangent line. Y is equal to 10x minus 25. Okay. Or whatever that's worth. So example 2 does not have a slide. So let's just clear this out of the way, and we'll do example 2 on this slide. Compute f prime of 3, where f of x is equal to x squared minus 8x. Okay? Now again, this is not the easy way to do derivatives. Later we'll come up with a far easier way to do them, but right now we've got to go back and do it the regular way. So, we want to compute f prime at x equals 3, but we first got to compute what f prime is. Someone remind me what that is. F prime of x is what? The limit. Let's go on and do f prime of 3. The limit as x approaches 3 of how does that go? Say again? And what? Okay. 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 Let me flash back here. We're going to use this form. X is approaching 3, so it's more like this than that. So it's alpha, the limit of alpha of x minus alpha of a over x minus a, right? Is that what you said? Oh, I thought you said, okay, I wasn't hearing you well, sorry. My hearing's bad. And getting on and off planes going up and down, my hearing it's going to clear one of these days, but it still has the, okay, so what did you say? Alpha of x minus alpha of a over x minus a. Now what's your a in this problem? 3. Okay, so that's going to be the limit as x approaches 3 of alpha of x. We know what alpha of x is. X squared minus 8x minus alpha of a. Well, what is alpha of a? Alpha of a is a squared minus 8a. But if x is approaching 3, that is our a, so this would lead to alpha of 3 being what? 9 a little louder, somebody. Minus, it's not that hard. This is 24. And what's 9 minus 24? Oh, those calculators slow you down, don't they? Minus 15. So the alpha of a is a negative 15. Well, it's minus a minus 15, which would be plus 15. Everybody see the magic there? Okay. Divided by I should have written this as a and then rewrite this as 3. That might have been a little bit better. This would be x minus 3. Right? The formal definition is alpha of x minus alpha of a over x minus a. We're wanting to know as a is 3. So you plug in the 3 there, the limit of, and we alpha of x, which was there, minus alpha of 3, which was there, and over x minus 3. What would you suggest doing next? Factoring. And can we factor that? We sure hope so. x times x minus minus. Everybody following what I'm doing? What are two numbers that multiply to be 15 and add to be negative 8? Negative 3 and negative 5. Okay, x minus 3's go out. And what's that limit? Negative 2. So that is your f prime of 3. Okay, is that what they asked for? Yes. So f prime of 3 is equal to negative 2. Okay. Now they did it with the f of a plus x. No, they did it strictly using the h form, which is fine. You can do it this way too. Both ways come out the same. It's equal to negative 2. All right. Everybody got that one? Any questions? Let's do example 3. They do have the picture of this one. Sketch the graph of f of x equal 1 over x. They didn't really, did they? They sketched half of it. The other half of it would be down in this one. Okay? They only sketched half of it. Okay? Why? Because they're only interested at x equal 2, so they weren't interested for the x equal negative numbers. But if they had sketched the thing, it would have been the other wing of this hyperbola down in the third quadrant. Look like a mirror image of that down here. They only graphed part of it. Okay? Showing the positive values for it, which is fine. Okay. And the tangent line at x equal 2. Now they've already shown that too. We need to calculate what it is. So they sketched the graph for us. Thank you very much. We need to do the tangent line. So if your f of x is equal to 1 over x, what is your tangent line? Give me the equation for the tangent line. Y, say again? Okay. L prime of A times x minus A. That's it exactly. Okay? They said, sketch the graph, they did it, and the tangent line at x equal 2. So what does that do to this form? Y minus when they say at x equal 2, that's at x equal a. So the a here is 2. So this will be y minus f of 2 is equal to f prime of 2. A is equal to 2 times x minus 2. Okay? Two things we've got to do here. What's that? Find what?
X.
F, you said? X. There it is. No, I'm fine. Okay. No, okay. We're going to leave it in the form of this. What we need to do is, what I meant was here. We need to know what f of 2 is, and we need to know what f prime of 2 is. We're going to leave it the x in there for now. Okay? Later we'll play. Because we're going to let x equal 2, aren't we? Yeah, we're going to let. So we know what x will be 2 ultimately. So we already found that. Okay. But what we need to do now is plug in and see what f of 2 is, and we've also got to figure out what f prime of 2 is. So which you want to do first? Hint, hint. Pretty easy to find what f of 2 is, isn't it? 1/2. Very good. Okay. Didn't want to make it seem hard. But finding out what f prime of 2 might be a bit more of a challenge. Let's first find out what f prime of x is. Can you give me what that definition is? Let's go on and leave f prime of 2. Let's go on and do 2. That's the limit as x approaches 2 of f of x minus f of 2 over x minus 2. Yeah, okay. Now, I think we know just about everything there we need. That doesn't mean it's going to be easy. X approaches 2 of, and what's f of x? 1 over x minus, what was f of 2? 1 over 2. And what's x minus 2? X minus 2. Okay? Need to calculate that limit, don't we? Remember the little trick we use for something like this? It worked, so we called it a method. Which of those is more complicated, numerator or denominator? Numerator. Let's deal with numerator first. We want to take on the hard stuff. Okay? What will we do to evaluate that numerator? Common denominator. I like it. And what would that be? I guess I'll write in the limit. I don't like to write a minute. X approaches 2 of. Okay, what's your common denominator? 2x. And what would your numerators be then? 2 minus x. Everybody agree with that? Over x minus 2. Right? Now, does anything look suspiciously possible here? Second? How do you do that? You flip it around. How do you do that? Okay. How about this? What if I factored out a minus sign? In that numerator. Factor out a minus sign, and that would leave a minus 2 plus x over 2x over x minus 2. Would you buy that? Did I do everything legally there? Okay? Now, can you rewrite this? What would that be? X minus 2. All right. So that would be the same as okay, minus x minus 2 over 2x over x minus 2. Now what can you do? Divide them out, right? You got to get that minus sign out of there. Okay? So this would be the limit as x approaches 2 of minus 1 over 2x. What would you do at this point? Plug it in, plug it in. And what does that give you? Negative 1/4. So there's your f prime of 2. Negative 1/4. I already figured out what f of 2 was, so now we can go back to this. Isn't that what we're looking for? Yes, we want the tangent line at that point. Okay? So this would be y minus 1/2 is equal to negative 1/4 times x minus 2. Okay? Y'all like the way that looks? No, it's ugly. Let's clean it up a little bit. Y minus 1/2 is equal to, let's first distribute the minus 1/4. What would that give us? Not that hard. Negative 1/4 x plus 1/2, right? Minus on minus is plus, right? Okay, and then what could we do? Add 1/2 to both sides, and that would give me y is equal to negative 1/4 x plus 1. Okay? Now, does that look like a line whose y-intercept looks like 1? That looks pretty good to me. And slope is negative 1/4. I think so. So sure enough, there's your graph of the tangent. Okay? And there's actually the formula for it. Y is equal to negative 1/4 x plus 1. See how that works? Don't we love doing the limits though? Isn't that the most fun part? Not. Okay? Let's see if we can do something about that. And by the way, they did it using the h, which is fine, but it just seems like it's so easy to do with the f of a form, you know. All right. One other sort of silly little thing here. Let's find the graph of a linear function and its tangent line. Didn't we already do that? Seems like we did it in the last, well, maybe we did. No, we didn't do derivatives because we weren't doing derivatives then. Okay. So let's do that. The graph of a linear function, let's see. Yeah, here we go. F of x equal mx plus b. There it is. Where m and b are some constants of a line with slope m. That's what the m is constant slope. B is the y-intercept, by the way. The tangent line at any point coincides, okay, they're giving us away there. So let's do that one. For this line, f of x is equal to mx plus b. Let's calculate what the tangent line is. You give me the formula for the tangent line, how we're going to do it. Would be the formula for the tangent line? Y minus what? F of A. F prime of A times x minus A. Perfect. Okay? Now, A here, they haven't given us a number. We're just going to use A, which makes it fun, right? So one of the first things we've got to do is find out what f of A is. And what is f of A? It's a lot easier than you're making it seem to be. Everywhere you see an x up there, you put an A in its place. So what would that be? M A plus B, right? Everywhere you see an X, put an A, right? Now, the other thing we have to figure out is what F prime of A is. And y'all give me that definition again. The limit as X approaches A of y'all gave it to me just a few minutes ago. rise over run, right? Alpha of x minus alpha of a over x minus a. Yeah, y'all gave that to me before. Okay. We have just written down what both of those are, so this is the limit as x approaches a of, what was your alpha of x? Mx plus b minus, and what's your alpha of a? Ma plus b over x minus a, right? All right. Which is the limit as x approaches a, right, of, let's clear those parentheses, be mx plus b minus ma minus b, right? Distributing that minus sign across, over x minus a, which is the limit as x approaches a of, guess what goes out up here? Plus a minus b, plus b minus b adds a 0. I can deal with that. And that, what have you got left up there? Mx minus ma over x minus a. Well, what can you do with that numerator now? Factor out the m. And what does that leave you with? X minus a over x minus a. And guess what? Gone. So this limit is? What's it again? M. Doesn't matter what a is. It's m. It's always m. The slope of a straight line is the slope of the line, which is m. Okay? So now we can plug that back into our first formula. Our formula here. Y minus, what was your alpha of a? Mx plus b. Okay? Yeah. No, ma plus b, sorry. Is equal to, and what was your f prime of a? M times x minus a. And guess what you get now? Oh, y. I didn't put what y is. Y is the alpha of x. So this is mx plus b minus ma plus b is equal to m times x minus a. You're just going around in circles, aren't you? Yeah, it's the same thing. It's identically the same formula. So the derivative of the tangent line is the slope of that tangent line, and the formula for the slope of the tangent line is the slope of that line, mx plus b. It's that, okay? Every place the tangent line is the line itself. Exactly. And that's all they were getting at. Which then led to these. Theorem 1 under derivatives. Derivative of linear and constant functions. If alpha of x is mx plus b, that's a linear function. That is a linear function. Then f prime of a is equal to m. For all a. No matter what a you put in there, the derivative is m. We did that just a minute ago. Now, what if alpha of x was a constant function? Alpha of x equals b. What would be its derivative? Why? Because f prime of this function is f prime of a, and what's the constant? What's the slope of a constant function? What's the slope of a constant function? 0. It never changes. So f prime of a is equal to 0 for all constants. Okay? If alpha of x is a constant, f prime of that function is 0. If f prime is a linear function, its slope is the slope. its derivative is its slope. Yeah. Okay? So let's do example 4. Oh, you can't tell me. Is it? Huh? Oh, how could it be? We're just beginning to have fun. Oh, we were always having fun. All right, we'll begin next time with example 4, right? Yeah. Oh, okay. Here's that. This is the graph of the second part of there. There is the graph of a constant function. Its derivative is always 0. Therefore, its slope is always 0, so therefore the derivative is always 0. Okay. They don't have a graph for example 4. So we'll start with example 4 next time and build on that. Did we get enough to... Oh, yeah, we got a few homework exercises here. Do number 1. I think you can do any of the odds 3 through 7. Okay? And it wants you to do them 2 ways, with the A's and with the H's. So try to do some with the H's. We didn't do any, but you can. Do any of the either 9 or 11. I think you can do both of those. I think you can do either 13 or 15. I think you can do both of those. I think you can do 17 or 19, both of those. I think you can do either any of the odds 21 through 27. I think you can do all the odds 29 to 45. And maybe hold off on the rest of them. We'll see. That'll be good enough to get going. Good deal. Any questions? We will see you, goodness gracious, once a week. Okay, no. Next week we'll see you twice. See you Monday. Have a good weekend.